presentation. I'm Gyeongchan from UNIST in the Republic of Korea. Today, I'm going to present JABAS, Joint Adaptive Batching and Automatic Scaling for DNN training on heterogeneous GPUs. This is an outline of the presentation. Now, I'm going to explain the background and motivation of this work. The common distributed training technique is data parallelism. I just clarified the terms of mini-batch size. Hereafter, the size of data processed by each GPU is local batch size, and the size of data processed by all workers is global batch size. I will call it GBS in short during the presentation. So far, fixed GBS has been used during training, which is referred to as static training. As synchronization becomes the bottleneck, large batch training has been applied. As shown in the figure, large batch training can increase the throughput compared to the small one. However, it shows the loss of final model accuracy. Therefore, to address this convergence issue, adaptive batching starts with small GBS, then increasing it during training. In the next page, I will introduce prior study on when and how to change the GBS. SemiGrad estimates gradient similarity metric to measure the stability of convergence. It is defined as the cosine similarity of aggregate gradients within two subgroups. As shown in the example, if it is lower than the threshold, increasing GBS might not degrade the convergence, so that SemiGrad can increase a GBS at the next iteration. As the metric is computed lightly to become reliable, SemiGrad can change GBS at iteration level. Therefore, we adopt SemiGrad as a basic method for adaptive batching. However, we observed that prior adaptive studies use static GPU resources. This caused a waste of resource. In the beginning, as GBS is relatively small, GPUs are underutilized by small local batch size and suffers from internal communication overhead. Therefore, it is necessary to scale GPU resource automatically according to the change of GBS. Recently, with the success of AI, GPU has been developed rapidly. Therefore, training on heterogeneous GPUs is inevitable. To utilize heterogeneous GPUs, prior studies perform data balancing by distributing local batch size differently according to the computational power of GPUs. In addition, they proposed a weighted averaging technique to avoid biased gradient. We call this work as WDP hereafter. However, it do not consider different gradient variance from different sample size. So, it violates independent and identical distribution, in short IID, which is a fundamental assumption of distributed SDD algorithm. The figure shows our convergence experiment of WDP. For static training, looking at the orange bar indicating the result of WDP, the models with the batch normalization had an adverse effect. Furthermore, the result of SemiGrad applied with WDP shows all of models suffer from convergence degradation. In summary, applying WDP for heterogeneous GPUs caused a significant convergence issue for both of static and adaptive training. So, instead of using different local batch size, our key idea is to decouple worker from GPU to process mini-batch of the same local batch size. Until now, I introduced the limitation of prior studies and our approaches to solve it. However, to adopt our approach, there are three main challenges. The first challenge is how to auto-scale GPU efficiently with adaptive batching. In addition, there are two challenges to introduce decoupling workers. One is how to improve GPU efficiency through multiple decoupled workers. Another is how to find complex configuration with decoupled workers on heterogeneous GPUs. Now, I present an overview of the proposed system, JABAS, to solve the aforementioned challenges. I will first describe JABAS in a nutshell and contributions of the system. Looking at the high-level view of the system behavior, at the early stage of training with adaptive batching, 4 GPUs are assigned for the small GBS. Here, we introduce a notion of decoupled worker, that is virtual stream worker, in short VSW, which utilize GPU multistream on a single GPU. And configuration solver assigns a number of VSWs to every single GPU. As the training progresses, the GPUs are additionally autoscaled at the next epoch. In JABAS, the amount of autoscaling GPU resource, for example here, 4 additional GPUs at the next epoch, is determined correspond to the predicted GBS trajectory by the GBS forecaster. Here, the point is, JABAS applies fine-grained adaptive batching at the iteration level and coarse-grained autoscaling at the epoch granularity. There are 3 contributions of the system. First, we develop the training framework, independent and identical data parallelism, in short IIDP, for heterogeneous GPUs to support decoupled workers efficiently while preserving convergence. Second, to maximize training throughput on IIDP, we present a configuration solver to find complex configurations of decoupled workers on each different types of GPUs. Last, we present joint adaptive batching and automatic resource scaling technique. Before explaining workflow of JABAS, I describe IIDP and configuration solver as 2 basic components of JABAS. Let me explain the overview of the IIDP. There's a heterogeneous GPUs A and B. GPU A has larger memory capacity and GPU B is faster than GPU A. IIDP leverages virtual stream worker using GPU multistream to execute the multiple DNN models on a single GPU. In addition, like GPU B, VSW can process multiple mini batches sequentially using gradient accumulation. On each GPU, the main VSW aggregates all of the local gradients by other VSWs. Then, synchronization is done by all reduce and updates new gradient to DNN model in each VSW. Through an effective synchronization method, IIDP achieves the comparable communication and optimizer overhead compared to naive data parallelism. The detailed mechanism is presented in the paper. Please refer to the paper. As shown in the example, IIDP requires different number of VSWs and GA steps on each type of heterogeneous GPUs. Therefore, we develop a configuration solver that finds it by dynamic programming with the objective of maximizing throughput. In the procedure, we also build performance prediction model to estimate an iteration time of various configurations to rank which one is better configuration. Now, I will explain the workflow of JABAS. First, user gives DNN model, hyperparameters, and GPU cluster information. For the initial GBS, JABAS first find the best VSW configuration and GPU allocation using the autoscaling manager and configuration solver. Then, this initial configuration is sent to the IIDP state manager and the job is executed on IIDP. During an epoch, for every predefined interval, each VSW participates in computing the gradient similarity metric. Then the metric is forwarded to the adaptive batching manager. Based on the metric, the manager determines the next GBS and the configuration solver gives the new VSW configuration. Then continuing the training. At the end of the epoch, the adaptive batching manager sends the trajectory of GBS during the epoch to the GBS forecaster. Then it predicts the trajectory at the next epoch. The autoscaling manager then uses the predicted trajectory to find the best GPU allocation for the next epoch with the configuration solver. Finally, training restarts with the changed GPU resource. That's all for the workflow. Next, let's go into more detail about the autoscaling mechanism of JABAS based on a predicted GBS trajectory. Figure shows GBS trajectory during training. Vertical line is the boundary of epoch. The GBS forecaster predicts the trajectory by adaptive batching at the next epoch. It used the previous GBS trajectory as data and then built from ensemble learning of Gaussian process regression model and exponential smoothing to take both advantage of prediction models. At the beginning of training, when JABAS receives the set of heterogeneous GPUs from user, it first generates all the candidate GPU allocations. With the predicted GBS trajectory for the next epoch, the autoscaling manager searches the best GPU allocation by estimating the epoch time with the configuration solver. If the best allocation is different from the current one, JABAS checkpoint and restarts the job for the next epoch. The experiment was conducted with 3 heterogeneous GPU clusters. The total number of GPUs on each cluster is from 16 to 32. On cluster C, to make a heterogeneous computation setup, we adjust the power of GPU at each node. We experimented with 7 DNN models, including the popular model for the Bison task and large language models including Llama. We compare JABAS with 3 adaptive training methods, SemiGrad, Pollux, and Pollux AS. Pollux AS employs an autoscaling policy followed in the original paper of Pollux. The figure shows the training time normalized to that with JABAS. The main result is that JABAS outperforms all baselines. It achieves about 33% time reduction compared to the fastest baseline SemiGrad for all DNN models across 3 clusters. ResNet and VIT are compute intensive and have small communication overhead. 3 LLMs on cluster C are also compute intensive. For this characteristic of models, JABAS utilize most or all of GPUs from the beginning. In this case, the main performance improvement comes from mitigating straggler via IIDP. Next, I will show the training cost result. Like training time, JABAS also outperforms all baselines for training cost. It achieves about 54% cost reduction compared to the second cheapest baseline on average. Here, for some models, Pollux AS achieves the second cheapest one due to autoscaling feature. In the case of GNMT, which is communication intensive, the below figure shows the average number of GPUs used during training for each method in cluster A. You can see that JABAS used the minimum average number of GPUs and it helps save the cost a lot compared to other methods. We observed that JABAS tends to minimize the use of with low computational capability to reduce internode communication. Note that there are several experiments in the paper. If you have any interest, please refer to the paper. In conclusion, we presented a novel DNN training system for a heterogeneous GPU cluster, JABAS. JABAS consists of IIDP, which provides the same theoretical convergence rate of distributed SDT. Our experimental results shows that without any accuracy loss, JABAS provides better performance in terms of training time and cost. Finally, source code of JABAS is available at GitHub. That concludes my presentation. Thank you for your attention. I'm happy to take any questions.